Welcome everybody in the room and online. Welcome to the Advances in Research and Innovation stream of the SNOMED CT Expo 2023. My name is Rory Davidson. I am the Chief Information Officer here at SNOMED International, and I'll be moderating today's session. All questions will be answered at the conclusion of this presentation. Online attendees, please use the Q&A button to type your questions to the presenter. And anybody here in the room, please use the microphone, as you can see in the middle at the end. I'm now very pleased to introduce John Grimes from the Australian eHealth Research Centre, CSIRO, who will be presenting a new tool for representing SNOMED CT concepts for use in model training. John's not here in person, but we have a video and he's here for questions and answers afterwards. So please go ahead.
Hi, my name is John Grimes and I am an engineer from the Australian eHealth Research Centre, which is the digital health program within CSIRO, Australia's national science agency. Today, I'm presenting on the topic of representing SNOMED CT concepts for use in model training, and I thank you very much for coming along. First up, I'll provide you some background on the motivation for this work. A section on techniques will follow, where I'll provide an overview of some of the different methods available for representing terminology concepts for machine learning. Next, I will take you through a set of experiments that we ran to evaluate different methods against a data set and a task. And then I'll provide you with a summary of the results of the experiments, along with some key takeaways. Finally, I will tell you about the future activities that we have planned to build and expand the work that we have started here. I want to start out by talking about an important activity that this work forms a part of. In recent years, we have seen major advances in the performance of machine learning methods across a broad range of tasks that are highly applicable to healthcare, including prediction, simulation, search, and synthetic data generation. We have these new machine learning techniques on one side and the world as we know it on the other side. At the intersection of the two lies feature engineering. Feature engineering is a critical part of any sort of data science or machine learning activity. At its essence, it is the application of domain knowledge to the task of translating raw data into numeric representations that can be used as inputs to model training and inference. Feature engineering can be as simple as deriving a numeric age from the combination of the date of birth and encounter start time fields. Or it could be the simple transformation of a categorical variable into a numeric vector. Or it could involve the use of another model that has been trained on other sources of data with learned information about how features in your data could be related. An example of this is the use of a large language model to create an embedding for a free text field. An embedding is a set of numbers that contains learned contextual information and can be oriented relative to other embeddings. And finally, it could involve the use of a clinical terminology to provide attributes and relationships that further describe codes and their relationships to one another. SNOMED CT is a knowledge resource that contains hundreds of thousands of concepts and has been curated by clinicians over the course of decades. It is a rich source of information about the meaning of diagnoses, observations, procedures, medications, and many other concepts routinely used in the recording of health records. The hierarchy and relationship information within SNOMED CT and other terminologies is routinely underutilized in the field of health data science. Our goal is to develop tools that make it easier to adopt and use this information in a way that improves quality and performance of models and analyses. To use clinical terminology within machine learning applications, it is necessary to transform each code within our data into a list of numbers, also known as a numerical vector. There are numerous techniques that we can use to achieve this. The baseline is the standard one-hot encoding that is commonly used for any type of categorical variable. We'll describe a method for extending this type of encoding to include information about hierarchy and relationships from the terminology. Then we will talk about techniques for making use of the natural language descriptions within the terminology. Finally, we will cover techniques for learning embeddings by training models on the structure of the terminology itself. One-hot encoding involves creating a table where each distinct code has its own column. We simply put a 1 in the column that matches our code and a 0 in all other columns. Each code is treated as being independent and not having any sort of relationship to other codes. We can extend the one-hot approach to include features from the terminology, such as the subsumption hierarchy. In this example, we have added additional information to convert our one-hot into a multi-hot encoding. Both nocturnal angina and vesicular ventricular tachycardia now share a feature that they are both types of heart disease. The presence of these features allows our model to learn associations with more general concepts than those that were directly captured within our data. Attributes and their values can also be encoded as features. Values of attributes can also have their own ancestor codes, which can be used to make associations with other codes that may not be directly related to them via subsumption. In this example, vesicular ventricular tachycardia has a finding site of left bundle branch structure. But because this is a structure of the heart, it also gets counted against this second feature that it shares with nocturnal angina. Use of these techniques can generate many additional features against your data. Evaluation is required to determine if these features are informative for the desired task. All the techniques discussed so far produce vectors that contain mostly zeros with a few ones. These are also known as sparse vectors. Sparse vectors are extremely common in the field of machine learning, and techniques have been developed to represent them efficiently. Instead of using memory and computation for every column in our table, we can use the more concise convention of specifying just the positions that are set to 1. Dimensionality reduction techniques also exist for converting sparse features into smaller, dense vectors. Principal component analysis is an example of an algorithm that can be used for this purpose. Here are some steps you can follow to build your own subsumption features using a FHIR terminology server, such as OntoServer. First, you need to define a scope. This requires thinking about the broadest set of codes that can possibly exist within your data or be required to be represented for inference in the future. You can then use the terminology server to retrieve all these codes. You might require all the codes within a system, or you may be able to restrict the exercise to a subset of codes. If you do use a subset, you will need to include all the ancestors of those codes. Then you create a one-hot encoding of all the codes in the scope. This will create a square matrix with a number of rows and columns that are equal to the number of codes. The next step is to feed the codes into the closure operation. This builds up a table of subsumption relationships between the codes. The closure operation will give back pairs. The first code subsumes the second. For each pair, we can look up the coordinates of the corresponding relationship within our one-hot encoded matrix and set it to a 1. Once this has been done for all the pairs, we will have a multi-hot matrix that represents all subsumption relationships between codes in the scope. Now we'll talk a bit about some alternative approaches to representing terminology concepts. An embedding is a numerical vector that captures and compresses meaning from some higher dimensional space. Text embedding models can take a word, phrase, sentence, or even a whole paragraph and produce an embedding. This embedding is based on observations of similar pieces of text in context within large volumes of training data. The distance between any two embeddings can be calculated to determine the relative similarity of the text that they were created from. This property allows it to be used for many tasks, including search, classification, and prediction. Embedding models have different capabilities depending on the character, quality, and volume of data that they have been trained on. Text embeddings can be created for codes within clinical terminologies using the descriptions, synonyms, and even natural language descriptions of the definition relative to other concepts. These embeddings can be used as an alternative to encoded relationship information, or they can work alongside. One recent innovation in the area of embedding models is instruction fine-tuning. This provides the capability to supply additional information within an embedding based upon its intended use. This could be used to orient a description or definition within the context in which it was captured. In this example, dog bite is not really a diagnosis, but it is routinely captured using the diagnosis field in many emergency departments. The second example might be used to embed a free text note for a cohort search and selection use case. HTN means hypertension within the context of a clinical note, but it might mean something different in another context. Finally, knowledge graph embedding approaches use machine learning methods to learn embeddings directly from the graph of relationships. Training data are provided as triplets, and the result is a low-dimensional embedding that can be used for tasks like link prediction. I'm still at the beginning of my journey in exploring these models and have not yet found a method that works well for SNOMED CT. We have done some experimentation with applying different types of representations to a simple task. The task is to predict the admission status for an emergency department encounter, given only the principal SNOMED CT diagnosis code. The data that we used is sourced from 5 hospitals in Queensland that have been capturing SNOMED CT data in the ED for a number of years. This task is overly simple and not very useful or realistic, but it has served a purpose in helping us to quickly gather knowledge across a broad range of techniques in this area. We generated a range of different encodings and embeddings, and then did a number of experiments involving the training and evaluation of classification models. These experiments included logistic regression and multi-layer perceptron models, and a broad range of different hyperparameters. Our exploration in this area is still in progress, and I'm presenting initial findings only at this stage. As part of the experiment, we created the following representations of the SNOMED CT codes within our dataset. One hot, which is a simple categorical representation with no additional information. FireTX, which is a multi-hot encoding of the ancestor relationships. No attribute information was included. Instruct is a text embedding generated by the Instructor XL model, which is an open source instruction-based embedding model. We used the prompt, represent the medical diagnosis for classification, and supplied it with the English preferred term. OpenAI is the ADA Text2 embedding model provided by OpenAI. Triplet BERT is a model developed by my colleague Hua No here at the Australian eHealth Research Centre. It is a BioBERT-based model that has been fine-tuned on triplets from SNOMED CT. It was primarily developed for the semantic search use case, but we have used it here without alteration as an initial experiment with a view to tuning it further in the future. And finally, we also tested a number of combinations of the FIRE-TX method combined with the text embedding methods. We ran a logistic regression model over each of these representations with cross-validation and an L2 or ridge penalty. The performance figures for the different methods don't show a large amount of differentiation on this task. We can see that the methods that include the subsumption hierarchy edge out the one-hot encoding in overall classification quality, but the improvement is marginal. The embedding models perform surprisingly well when supplied with the preferred terms, and combining them with the encoded subsumption hierarchy seems feasible and desirable. In relation to the small margin between one hot and the other methods, one theory is that this can be explained by a large overlap between the codes in our training and test sets, which would give the one hot method an advantage. To test this, we ran the models again, but this time instead of an 80-20 train test split, we flipped it around and held out 80% of the data for test and used only 20% for training. The results showed that the margin between one hot and the other methods increased when we did this, which indicates that all of the other methods have a better ability to generalize to unseen codings. Even though our task was not terribly successful at differentiating our representations, there are other techniques that can offer some insight into this. Dimensionality reduction techniques can perform unsupervised learning on our high-dimensional representations and boil them down into a lower number of dimensions. For these examples, we have used a model called UMAP, which stands for Uniform Manifold Approximation and Projection. Here we have used 3 dimensions so that it is possible to visualize the distance between concepts. As you can see, one hot is just random, while all of the other methods make an effort to group together and minimize the distance between related concepts. The FIRE-TX model groups concepts together unambiguously according to the presence of hard subsumption relationships, while the embedding models seem to have more nuanced relationships that are reminiscent of the natural language that they are derived from. We can zoom in and explore our representations to ensure that we are getting the correct groupings. Here we have identified a group of concepts that are all types of drug toxicity. And now that we have a way to encode any concept, why not do it for the whole terminology? Let's zoom in to the Australian edition. These are all disorders affecting the larynx. These are fungal antibodies. These are tendon structures in the lower limb. And these are types of intestinal biopsy. As of today, the Australian eHealth Research Centre has released a new open source library for encoding any type of FIRE terminology for machine learning applications. It's a Python library and it can be used standalone or as a step within a scikit-learn pipeline. It currently supports subsumption relationships, and you can request the property types you would like encoded alongside. SNOMED CT attributes are modeled as properties within FIRE and can be requested using their SCT ID. It does not currently support attribute value subsumption or transitivity. The encoder returns a multi-hot sparse vector, which you can then combine with other features, as we showed in our previous example of combining the subsumption hierarchy with natural language embeddings. You can follow the link or scan this QR code to find out more. There is so much more to investigate along this theme. We're planning to apply these techniques to a more significant task with established feasibility and clinical value, such as the prediction of rehospitalization. This could involve assessment of the utility of current and historical SNOMED CT diagnoses and procedures. Another technique that we would like to investigate is the supervised training of embeddings that include information from health records, such as co-occurrence. We would like to enhance our solution for encoding attributes to include value subsumption and also transitivity of attributes to bridge across the different hierarchies within SNOMED. And finally, we would like to evaluate the performance of embeddings produced by knowledge graph embedding techniques to complete our survey of the available methods. In conclusion, I think that the activity of feature engineering is something that we need to support both as tool makers and also as a standards development organization. This is where the rubber meets the road in terms of application of SNOMED CT within data analytics and also return on investment in data capture. Our initial investigations suggest that the representation of SNOMED CT relationships seems useful for training models, but we need to do more work in this area. And finally, language models are likely to play a significant role in helping to represent SNOMED CT within machine learning, if only to surface the value within the huge volume of descriptions and translations that exist within the terminology. Thank you very much for your time and attention. I appreciate your support and would love to hear any feedback you might have.
Thank you. John will now take some questions. He is online to hear us. If you're in the room, please step up to the mic in the middle behind the camera. We have some questions for you, John. Over to you, Kinwa.
Hi, this is Kinwa Fong from National Library of Medicine. Thanks for the interesting presentation. So one thing that stands out from your presentation is that from your visualization results, it seems that you have a very distinct pattern for each of the embedding approaches. That one of them separates the concepts in clear, distinct clusters, while in a hot approach, you have a big glob of concepts. So, and I was a bit surprised to see that actually the results of your evaluation, the different approaches really, don't have much difference. I wonder if you have carried out any failure analysis to see why some of the better distinguished embeddings do not yield better results?
Yeah, so I think it's mostly down to the task. It's a pretty simple task. It's basically just predicting the admission status. And one problem with it is that the people capturing this diagnosis are basically capturing it almost at the time of admission. So it's almost, something that's being captured at the same time as we already know whether they're admitted or not. And there's single codes that correlate very, very highly to either admitted or not, even without the help of any sort of subsumption relationships. So it's not a really great task for showing off the utility of the subsumption hierarchy. So we're looking forward to trying this out on something a little bit more complex that requires a little bit more clinical nuance, like readmission, and where we can mix in multiple SNOMED codes, historical SNOMED codes, also procedure codes. I think we will start to see more of a distinction there.
Are there any questions, other questions in the room? We have one question online, which was somebody was asking for you to share the link, John, if you can, to the open source that you just announced as well.
No worries.
If you see the Q&A on the webinar, you should be able to see that. Okay. Thank you. So a couple of questions from me. So what plans do you have to enhance it from here? I mean, this is the kind of the early starts to work, like you said, there's a lot to do. Where are you going next with some of this stuff?
So as I say, so we've currently, our lab has developed a readmission risk algorithm on the top of Queensland health data. And we achieved quite good performance without any diagnosis codes at all. So we actually assessed DRGs, which is like a derivative of the ICD code that clinical coders come in after the fact and add. And perhaps unsurprisingly, that didn't add a lot of value, but actually no SNOMED CT data was used at all, even though we have SNOMED CT diagnoses and procedures. So I think there's an opportunity there to evaluate whether that SNOMED CT data adds to that model. And like I say, it's a non-trivial use case, and I think there's an opportunity to test whether the ontology behind the SNOMED codes is actually adding value to something that should involve that should get some benefit from that additional clinical detail, I think. And also just continuing to work on the methods. There's still a lot of work we could do there, including things like attribute transitivity. So for example, with the Australian medicines terminology, relies heavily on attributes. And if we can follow those attributes through between hierarchies and find some additional relationships there, that could be another thing to try.
Great, thank you very much. So with that, I think we will conclude the session. Thank you very much, John. Fascinating talk. Shame you can't be here with us, but maybe next time. Online delegates can join another session through the event lobby. So thank you, John. Enjoy the rest of your day.
Thank you.